This conference will now be recorded.
So very good evening, students. Today we are continuing with discussions on the ray optics part. So let us solve few problems on this. So this problem is related to refraction. So this says a transparent slab of thickness D has a transparent slab of thickness D has refractive index n of Z that increases with Z. You see this shaded part. This is the slab which has vertical thickness Z, and this refractive index, if you see, this is actually varying. This is function of Z. That means refractive index is increasing from this side to this side. Okay. So here Z is the vertical distance inside the slab measured from the top. The slab is placed between two media with uniform refractive indices N1 and N2, where N2 is greater than N1. So here N2 is greater than N1. The thing is that this is a medium which has refractive index N1, and this is another medium which has refractive index N2, and in between this is sandwiched. So a ray of light incident with angle theta I, a ray of light incident with angle theta I, as you see here, from medium 1 and emerges in medium 2 with angle of refraction theta F, and there is a lateral shift as well. Lateral shift is given as L. Here it is L actually. This is not I, this is L. Lateral shift is L for this ray. We know very well there will be a lateral shift when this ray goes through the slab. And if this N1 and N2, if these two are actually same medium, in that case, this ray and so incident ray and emergent ray will be parallel to each other like this. Okay. In case of the medium in which the slab is kept is the same. Okay, in the same medium if you keep, then there will be lateral shift, and that lateral shift is this. In this case, this is the lateral shift L, and in that case actually the ray of incident ray and the emergent ray, they will be parallel to each other. But in this case you see the medium is not the same. Here on the top there is some other medium, and At the bottom there is some other medium. Okay, so here one medium, another one is here. So that's why these two rays are not parallel to each other. So that's why theta I not equal to theta f. So that's what we can say from this figure. Anyway, which of the following statements is true or are true, we have to find out. So what are the options? The first option says L is dependent. L is dependent on NZ. L is dependent on NZ. Okay. This option, see, we know this is correct actually, because L will depend on both this medium N1. In fact, this is small l. The L is the lateral shift. This depends on both the medium where the ray incidents and the medium through which it travels. Okay, so that's why this is correct. Now let us see. So here, if we apply Snell's law, then see, we just write this first medium, then sine of the angle of incidence in the first medium, then refractive index of the medium where the light emerges, okay, into sine of the angle of refraction, that is f over here. So this is actually the angle of, sorry, this is Snell's law. This is Snell's law. This is called Snell's law, and this law has to be written in this way, and hence the option C is also correct. Okay, option C is also correct. But this option n2 minus n1 into sine theta f, this is not correct. Okay, if we want to write Snell's law, we could have written n1 sine theta 1 and some nz. Actually, see, this nz is not n2 minus n1, so that is not the way. So we can write for this place, this particular medium, nz into sine of some other angle. Anyway, if we had this angle of refraction inside the medium, if we would have been given some informations about this angle, then we could have written like some other angle, some intermediate angle, okay, sine r say. But again, this nz, we know this Snell's law is actually valid for the two medium where the refractive indices are not changed. So actually we can use this Snell's law only when we have refractive indices constant, okay, for the medium. So anyway, this is not true. Now L is independent of N2. See, refracted ray, this refracted ray is obviously, the angle of refraction obviously will be dependent on the medium where the light ray is emerging, but the lateral shift, it depends only on these two. medium 1 and the medium through which the ray travels. So that's why this L would not depend on this N2. So lateral shift will not depend on the refractive indices of the second medium. Okay, so now then what we get here, we have got L is independent of NZ. Okay, this is sorry, L depends on NZ. L lateral shift depends on NZ through which it is traveling, and this is the correct Snell's law for this particular problem or figure. Okay, not this one, not okay. So these are correct options here. A and C are correct option here. We'll go to the next problem. So this is from JEE Advanced 2017, and this is a very nice problem. In case of JEE Advanced problem, there will be actually more than one correct answer. Okay, so you have to choose how many are correct over here. Okay, which are the correct options, whether okay, whether any one option is correct or multiple options are correct, so that you have to see. First of all, let us read the problem. So this problem says, for an isosceles prism of angle A, angle A for an isosceles prism of angle A and refractive index mu, it is found that angle of deviation delta m is A. Which of the following options is or are correct? So first of all, we have to understand this thing, that we have an isosceles triangle. Okay, so sorry, prism, triangular prism. So you can see this is kind of isosceles triangle, and this AB face and AC face, they will act as refracting surface, and this is the prism. And you see, in this case, the question is uh, refractive index of the material of the prism is mu. Okay, and minimum deviation, angle of minimum deviation delta m is A. When okay, so which of the following options are correct? Okay, let us read first the option A. For the angle of incidence I1 is equal to A, the ray inside the prism is parallel to the base. Okay, so this we have to prove. So this is true when R1 is equal to R2. Okay, and we know in case of minimum angle of deviation, actually minimum angle of deviation can be written as I1 plus I2 minus A. Sorry, this is so we have I1 plus I2, or yeah, I2 minus A is equal to delta M, and since delta M is A, okay, delta M is A, and you know, like in case of minimum angle of deviation, I1 will be is equal to I2. That means, see, I1 means this one, angle of incidence, and I2 means angle of emergence. Okay, so at minimum angle of deviation, minimum angle of deviation, delta M, I1 is equal to I2, okay, and R1 is equal to R2, and that is always actually A by 2. R1 is equal to R2 is equal to A by 2. Okay, so I know this relation delta M is equal to I1 plus I2 minus A. Okay, so these are 2A, then sorry, 2I. All right, this is 2I minus A, 2I1 say. This is delta M is again given as A. So I1 is 2A by 2, that is A. Okay, so I1 and I2 will be equal to A. That we have understood. All right, now we can actually have a relation between I1 and R1 from here. If I give this as 1 and this as number 2, then we can draw a conclusion that R1 is equal to I1 by 2. Okay, we'll just keep this for now as equation number 3. All right, now look at the options. The first option says for the angle of incidence I1 is equal to A, the ray inside the prism is parallel to the base of the prism. Actually, this is true, because when I1 is equal to A, in this case, since the delta M is delta M is A, that's why when I1 is equal to A, that time this R1 and R2 are equal, and that is I1 by 2 or A by 2. Okay, If this R1, see this is R1 and this is R2, if these are same, then this ray will be always parallel to the base of the triangular prism. So that is what is said here. So this is correct. I'm just writing the correct as C, correct option. The second option, let us see, at minimum deviation, the incident angle I1 and the refracting angle I1, sorry, R1 at the first refracting surface are related by R1 is equal to I1 by 2. This also I have showed you here. R1 is equal to I1 by 2. So this is also true. This is also true. Now, we have angle of incidence. Okay, for the prism, the emergent ray at the second surface will be tangential to the surface is, see, for this prism, the emergent ray at the second surface will be tangential to the surface, then I1 will be sine inverse sine A whole into cos square 4 cos square 2 by A, sorry, A by 2 minus 1 minus cos of A. Okay, so this is the option. We have to see whether this is correct or wrong. Okay, see, when the ray is tangential, look this figure. I'm just erasing everything. Look this figure. When the ray is tangential to the surface, second surface, that means second refracting surface, that means this angle is 90 degree. Okay, this is 90 degree. That means, see, if I just consider this refracting surface AC, consider refracting surface excuse me, refracting surface AC. Consider the refracting surface AC. So in this case, look, if this is tangential, the emergent ray is, or refracted ray is tangential to the refracting surface AC. That means what? At to see R2 must be some critical angle for this particular interface. Okay, so theta R2 must be a critical angle. R2 must be a critical angle for the refracting surface AC. So this is not very tough to understand. Again, we know R1 plus R2 is equal to A. Okay, that is what we know. So at minimum angle of deviation, R1 is equal to R2. So R1 or R2 will be equal to A by 2. So in this case, what we can write? We can write R1 is equal to A minus R2. See, R2 is what? Let us give this equation 1. Give this name. Okay. So R1 is equal to A minus R2, which is A minus theta C. A minus theta C. Right? So we have got R2, we have got R1. So this is R2, this is R1. Okay, and this angle is 90 degree anyway. We know we can apply Snell's law to find out Snell's law over here. to find out what is mu. So Snell's law, if we'll write 1, see refractive index 1 for this particular surface. Okay, this is in the vacuum or in the air, that's why. So sine I1, because we have to find out I1, sine I1 is equal to N2 sine R1. Okay, N2 means, let us say this is mu, as the index is given. Okay, anyway, this is sine mu sine R1. So what is R1? We know this is mu sine R1 means A minus theta c. Okay, now so what is I1? Then this is sine I1. Okay, now I1 will be sine inverse this part. Okay, sine inverse mu whole into this sine, okay, the sine A theta c. Okay, this will be one thing. So we have to now show this thing. I think before we go for this option, let us see whether this happens. Okay, let's see this option first. Okay, so refractive index of the prism, how it is related. Let us just see mu is equal to sine R1 by sine I1. Okay, so that means sine I1 is generally, see here sine I1 is given already, that is sine A. Okay, sorry, A, I1 is A, we have already shown you I1 is A. Sine, what is sine R1? Sine R1 was actually this. Oh, I'm sorry, here it will be just inverse of it. I'll just go to the next page. If I write Snell's law for the first phase, so it will be mu is equal to sine I1 divided by sine R1. Okay, so it will be, see, sine A, because I1 is A, and this is sine A by 2. Okay, now we have this option. The last option is A is equal to what? We have to find out what is A. Let us see. This is actually sine. Let us break this one. trigonometrically. So this is the one, and this is again, this is equal to mu. From here, this sine a by 2 sine a by 2 will cancel each other. So 2 cos of a by 2 is equal to mu. Okay, this is equal to mu. Okay, so if this is mu, then cos of a by 2 must be mu by 2. Then a by 2 again will be cos inverse mu by 2. Okay, or a will be actually, this is half is there, so it will be 2 into this, 2 into cos inverse mu by 2. And see here, option, in the option it is actually half. It should not be half, so this is not correct. Okay, this is not correct. So now look this option, you will be able to get it. Okay, we had, we were here. Okay, we have to see what is mu is equal to this. We can just use this part. Okay, or we can use even, see, cos of a by 2, cos of a by 2 is equal to mu by 2. We can just find out what is uh, sine a by 2. Okay, from here, a by 2, so it will be nothing but 1 minus cos square a by 2, right? So that we can use this kind of identity, trigonometric identities, and try to get that. Okay, so what we have got up to here, we had this equation. We'll write this equation. Let me write this. I1 is equal to sine of a, sorry, sine inverse sine of a, sine inverse sine inverse from here, sine inverse mu into this. I1 is equal to sine inverse mu into sine of a theta, sorry, sine of theta minus a minus theta c. Okay, a minus theta c. So from here we have to, so if we just break this, sine inverse mu sine a, let this be mu as it is, sine a cos of theta c minus, so sine a, so here it will be cos of a sine theta c, right? So look, this sine of a, this part is fine. What is cos theta c? Cos theta c This is sine theta c. We have got here sine theta c. See, if we go from here, theta c means sine r2 is equal to 1 over mu sine of 90 degree. Okay, so it is 1 over mu. Sine theta c means 1 over mu. Okay, if you look that sine theta c means 1 over mu. Okay, then what about cos theta c? We have to find out that. So what is cos theta c? If we have sine theta c, okay, let me write it here. So we have sine theta c is equal to 1 over mu. Okay, so that we can write over here. What about cos theta c? Cos theta c will be 1 minus sine square theta c. That means what? Or let us use this now here. So if sine theta c, okay, we'll otherwise we'll just directly write. Okay, here at least let us write this first. Sine inverse. This is mu. Okay, so this is sine A. Cos theta c, let it be here. This cos of A is fine. This sine theta c will write as 1 over mu. Okay, now we had actually sine theta c is equal to 1 over mu. This is the one. If cos theta c is again, it will be 1 over, sorry, square root of 1 minus 1 over mu square. Okay, if we write this, then we get actually 1 over mu, and this is mu square minus 1 in the inside the root of r. Okay, you can just look at here. What I have done, we know sine theta c is equal to 1 over mu at the critical angle. So cos theta c will be 1 minus sine square theta c, that is 1 over mu square. And see, I have just simplified a bit. Let me write again sine inverse sine inverse mu, let it be here, this sine A, let it be here, cos theta c, in place of cos theta c we'll write this 1 over mu square root of mu square minus 1. Okay, then this is cos of A over mu. Now look, if I multiply this mu, then this will be getting cancelled with this. So I would have here a form, nice form, that is sine of A into mu square minus 1, and this is cos of A. See, we have reached nearby. Look, this option in the figure, sorry, question. See here, instead of mu something is there. Okay, look, in this option we have already proved previous option. See, we have proved that is equal to so from this option, see, this option here, mu is 2 into cos square a by 2, sorry, mu into cos of a by 2. That if we put it here in this, okay, so far we have got, so we had already proved that mu is equal to 2 into cos of a by 2. So that is what we have proved. Okay, now we have got I1 angle of incidence at the first interface is sine inverse. Mu has already gone. There is sine A into this, and this is cos of A. So this is what is remaining now. In place of mu, we'll put this. Okay, this 2 into cos of A by 2. Then what we get? Sine of A, and this is 4 cos square A by 2 minus 1 minus of cos of A. Okay, so this is very true. You look, this is this option which is given in the last option, oh sorry, the third option. See, this third option, I1 is equal to sine inverse whole into sine A into cos square, sorry, 4 cos square A by 2 minus 1 minus cos of A. This is actually true. So we have got A, B and C. These are right options here. Okay, now we'll pick up some other problem. Okay, so we'll pick up some more problem. See, question number 3. I write it here. Choose the correct statement. Choose the correct statement. First is the speed of light in the material is the speed of light in the metamaterial is V is equal to C modulus of n, where n is actually refractive index. First option. The second option, the speed of light in the metamaterial, the speed of light in the metamaterial is V is equal to C by modulus of n. Third option is the speed of light in the metamaterial is V is equal to C, and the fourth option I'm writing it here. The wavelength of the light, the wavelength of the light in the metamaterial lambda m is given by lambda m is equal to lambda air whole into n, where lambda air is the wavelength of the light in air. Actually, this is a question from a passage. I'm not giving the passage over here. You can get it. I'm just writing the question number. It is actually from JEE 2012. Problem number. Sorry, this is the problem. JEE 2012 paper. So this is a passage-based problem. There is a passage about metamaterial having refractive index n greater than 1. So when light ray from air enters in naturally occurring material, then Snell's law, we know n1 will be equal to, sorry, n1 sin theta 1 will be equal to n2 sin theta 2. It is understood that the refractive index bends the light towards the normal, but never emerges on the side of the normal as the incident ray. So according to electromagnetic theory, the refractive index n is equal to c by v, that we know. C by v. C is the speed of light in the air and v is the speed of light in the medium. And this is equal to plus or minus square root of epsilon r and mu r. This is mu r. Okay. Where c is the speed of light in vacuum and v is the speed of light in the medium, and epsilon r is the relative permittivity and mu r is relative permeability. Okay, so these are few informations we can have, and with this we have to solve this problem. So let us try to solve this problem. First of all, the first option is seen here. The speed of light in the metamaterial v is equal to cn, v is equal to cn. it may not it must not be true, because we know v is equal to c by n. Okay, c by mod n, but it is given v is equal to cn. It will be c is equal to vn. So the first option is not correct. Okay, the speed of light in the metamaterial this is not correct. The speed of light in the metamaterial is v is equal to c by n. So this is correct option. Okay, this is correct. Option C says speed of light in the metamaterial is c. This is also not correct, because you know the light will be while traveling through material, the speed will be altered, and because of that, the 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 speed of light in vacuum and the speed of light in the medium, in any medium, will not be the same. Okay. Now the last option is that the wavelength of the light in the metamaterial is given by this. We can just see whether it is true or not. How to see that? See, we know lambda is equal to okay, c is equal to, or v is equal to nu lambda. We'll write v is equal to nu lambda. V is equal to nu lambda. Speed inside medium nu into lambda medium. See, this is very interesting, that nu, or the frequency of the light, never changes. Only change happens in the wavelength and in the speed, but not in the frequency. Frequency does not depend on uh, the refractive index. Okay, in fact, frequency is actually the one which remains same for all the medium for a particular light. So if I write c also can be written as nu into lambda ar. Okay, so refractive index is c by vm. C by vm, we know that. So then if we take the ratio, if we take the ratio this c by vm, then what we get? Nu lambda ar is equal to nu lambda m. This goes, so lambda ar will be lambda m into refractive index. So this is actually true, but this is not true. So this is not true option, because we know this will be true. Okay, the wavelength of the light inside. Okay, so it will be actually larger. Wavelength will be larger. Wavelength will be sorry. I'm sorry. Wavelength is actually, see, medium. Inside the medium it is less, because travels less. Okay, and here it is more. But here this shows different. Okay, this shows different. Lambda. This problem is saying that lambda m is greater than lambda r, but that is not true. Why? Because they travel a very less distance inside the medium. Okay, so there is no way to to become this. Okay, lambda m always will be less than lambda ai. So that is the thing. Okay, so we'll have one last problem for today. So that is related to the resolution of the astronomical telescopes so the question is calculate the limit of resolution, the limit of resolution of a telescope objective objective having a diameter having a diameter of 200 centimeter. Sorry, this is 200, yes, centimeter. If it has if it has if it is if it has to detect if it has to detect the limit okay, so just a minute. If it has to detect wavelength, the light of wavelength 500 nanometer coming from a star, coming from a star. So we have to calculate the resolution. How to find out that? Actually, we can just, for the sake of solving this problem, we need to remember a simple formula for finding out the resolution of telescope. What is this formula? The formula is actually this. Okay, let me just write the formula, then we'll see the, let us solve this first, then we'll see the options. So the formula for the resolution of a telescope is given, if the telescope objective is given by delta theta. This is very simple formula, you should remember this. to solve this problem. But if you want to read how it comes, then you have to go for the detail. So what is lambda? Lambda is the wavelength of the light coming from stars, which is given here. D is the diameter. D is the diameter of the objective lens. That's all will give you the answer. This is a very simple problem, but it had been asked in 2019 JEE mains paper. So this formula is very important. So resolution of a telescope is given by this. So lambda is given. We will just write this lambda 500 nanometer. Let us write this as 10 to the power minus 9 meter. And in the down, see down we have diameter 200 into 10 to the power minus 2. This goes in here. This will be 10 to the power 11 order. So this we have to multiply. See, okay. So this is 0.6 into 0.61. 0.61. If we divide this with 2, then multiply with 5. So 5. This is so 3.05. Okay, 3.05 into 10 to the power. Okay, this is not 10 to the power 11. This actually 10 to the power minus 7 meter. Okay, then we have to see the options. How? Oh, I'm sorry. This is not even in the meter. This is actually theta. That means it will be in the unit of radian. Okay, this is rad. This is radian. Okay, so 10 to the power 7, and if we write in terms of 10 to the power 9, then it will be 305 into 10 to the power minus 9 rad. Okay. 305 10 to the power 9 rad. And see the options were the options were 610 into 10 to the power minus 9 rad. Option B was 305 into 10 to the minus 9 rad. Option C was 457.5 into 10 to the power minus 9 rad. And option D was 152.5. Okay, so among this option is true. All right, so this is very important, and we have to remember this formula for telescope. Okay, this is for telescope. All right, we'll stop it here for today. Next day we may learn some other chapter. Thank you very much for your attention. Bye for today.